All right, we're back with section 2. It's a really short section, but a really long title. Magnetic dipoles, monopoles, ferromagnetic, paramagnetic, and diamagnetic materials, okay? We've never seen a magnetic monopole before. Wait, let's break this down real quick, okay? Monopole, a magnetic monopole has never been observed, okay? And we don't really they're not included in the current laws of physics, but I do want to kind of talk about them just really quickly, okay? You should know, you can break down this word, right? Monopole. What does mono mean? Okay? Mono means one, and pole means pole, okay? Okay? So that means one pole. So if it was a magnetic monopole, how would you expect it to look? It would either have just a north or just a south pole, okay? It would not have both, okay? It would not have both. It would only have one or the other, okay? Because, you know, mono, pole, okay? What about a dipole? What does the prefix di mean? Di means two, and pole, you guessed it, means pole, okay? So it means that it has two poles, right? Okay. An atom is technically a magnetic dipole because of the spin of electrons orbiting the nucleus, okay? I'm going to talk to you about this, and you're not going to understand the rule that I'm basing this on quite yet, okay? But I'm going to get to that, I think, in the second section, okay? So what happens is, where's my blue pen? It's in my Ziploc bag. I keep all my pens in a Ziploc bag because one day I'll buy an actual bag, okay? Just not today. Okay, so let's say that we have the nucleus with an electron orbiting it, okay? So here's our nucleus, okay? And we have an electron orbiting that nucleus, okay? And let's say it's orbiting counterclockwise, okay? And I want to be clear here, okay? This is orbiting in a way that is perpendicular to the plane of the page. And what do I mean by when I say the plane of the page, right? If we were to, you know, the page is a plane, right? So what it's doing is it's orbiting. When it's orbiting, it's actually coming out of the page and then turning and going back into the page. And so it's making this, you know, if I were to take my paper, right, and, you know, hold it vertically, right, it's actually going, or you can't really see that, it's actually going perpendicular to the page, right? It's not on the page. It's going perpendicular, right? And that notion of into the page, out of the page is kind of confusing, or plane of the page is kind of confusing for a lot of kids. So that's kind of my best way to explain it, right? Is that this is making circles perpendicular to the page, right? So the circle it's making is perpendicular to the paper, okay? So it's going into the page, out of the page, into the page, out of the page, okay? Now, I'm going to use my right hand. There's a rule that we have in physics called the right hand rule, okay? That when we have, we usually use it to determine direction of magnetic fields, okay? And this is a grip rule. I'm going to teach you that in the second section, okay? I'm not doing the Aggies thing, and I'm not agreeing with you. I'm just doing the grip rule, okay? And what you're going to do is, since this is what we have here, is we have a negative charge orbiting it. Oh, wait a minute. It's a negative charge. So when we actually have negative charge, we actually have to use our left hand, okay? I know that this doesn't make a lot of sense to you right now. Again, if you want, I would suggest you watch the section 3 video because I talk about the right hand rule in there, okay? So what's going to happen is if it's orbiting, you know, into the page, out of the page, I curl my fingers in the direction of its orbit, okay? And then my thumb points in the direction of the North Pole. So we would see that right here is actually the South Pole going up and the North Pole going down, okay? And then you know, again, if let's say the nucleus was orbiting in the opposite direction, okay? So here it is, it's going like this, okay, and then around, okay? Let's say it's orbiting the opposite direction again. You would use the right-hand rule, okay? It's going perpendicular to the page, out of the page over here, into the page over there. It's going up, okay? So then we would have the North Pole going up and South Pole going down, okay? Okay, there's a lot of just kind of blurb here, okay? But what it's talking about is there's 3 different types of materials. So what happens is if you have a solid, okay, when all of the atoms of a solid, so when you have a substance, enough atoms of a substance that combine into a solid to make anything really, could be like cardboard box or Lego bricks or something like that, right? When all of the atoms of a substance combine to make a solid, okay, there's a ton of magnetic domains on that solid, okay? I'll give you an example, right? Here's a block of wood, right? Okay. And what you don't see is that there's actually a bunch of little like regions on here that actually have a ton of atoms. Obviously there's a bunch of atoms, right? Those atoms form these little regions called magnetic domains, okay? Not Gojo, right? But we're talking about magnetic domains. And these are these little regions on the solid where all of the dipoles all agree on their direction. So you might see an example right here, right? You have, it's really hard to see, but you might see right here that you have these little dipoles, okay, or these little regions, okay? I can't really highlight it all too well because I can barely see it myself, okay? You have all these little regions, okay? You can probably see it if you have a physical copy of the paper, you can probably see it pretty well. But we have all these little regions, and inside those little regions, or those little sectors, okay, all the dipoles all agree on the same direction. So for example, right, in this bottom left region, they're all gonna go down to the left. This region up here, they're all gonna go up to the right. They all agree on their direction, they're all going to orient themselves towards that direction, okay? Now, depending on the substance, okay, when we apply a magnetic field to that object, okay, depending on the substance, when we apply a magnetic field, those domains are going to, or those dipoles are going to reorient themselves, and it depends on the type of substance, okay? So let me give an example, okay? Let's say that I apply a magnetic field across all three of these materials, and it's just directly to the right, okay? Okay, there you go. This is what we call a B field, right? B is magnetic. I know it's not, it's confusing. Why is it not an M field, okay? It's a B field, okay? I'm Mr. Mitchell. If I come up with something in physics, then I'll call it the M field, okay? Because, right, I'm Mr. Mitchell, right? Okay. Ferromagnetic materials have their domains aligned with the external magnetic field very strongly. So we're applying an external magnetic field or an external B field, okay? And that's going to cause the ferromagnetic dipoles or the ferromagnetic domains to align with that very strongly. So what's going to happen is you're going to see all of these domains, they're all going to align with it very strongly. So they're all just going to point directly to the right now, okay? And you can actually permanently magnetize a ferromagnetic material, okay, if you keep them aligned, okay? And you can see that's kind of what happens up here, okay? Paramagnetic materials have their domains aligned very weakly. Okay, so what's going to happen is these are going to tilt in the direction of the B field, but only just a little bit, okay? Oh, that one kind of went a lot, right? Okay, they're only going to tilt just a little bit in the direction of the B field, okay? They want to go all the way, but the material's not going to let them, okay? And the diamagnetic, this one's kind of an interesting one. Diamagnetic materials have their domains aligned opposite the external magnetic field. Oh, okay. So they align. So there's aligned with very strongly, with very weakly, and then opposite very weakly. Oh, sorry. Did I say opposite very strongly? I meant to say opposite very weakly. Okay. And so what's going to happen is these are actually going to be deflected away from the B field direction, so it'll go something like that, 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 that, and that. Okay, makes sense, right? They're kind of pointing away from the B field. They're rebelling. Okay, all right. That's that. Have fun.